Hi, my name is Noah Gift, and I'm the founder of Pragmatic AI Labs. In this course, we cover analytics with AI on AWS. And it's a very exciting course, not because AI is magical, but because AI has an enhancement towards traditional analytics pipelines. A few of the things that we talk about include the foundational security models of AWS, some of the core services for AI, including Amazon Q, Amazon Bedrock, uh, Data Wrangler, and also services like QuickSight that allows you to do ad hoc business intelligence. What we discover when we're doing things with AI is that it's really an enhancement of what's already there. So it's as good as what you already have. If you have existing processes that are good at deriving insights, or you have strong methodologies in software engineering and you want to do profiling for costs, this is where AI comes into play and saves you time. One of the things that was covered in this exam that was really interesting is that we were able to build out a prototype that showed that we could save 10 times the cost. And after we were doing the benchmark, we took that benchmark data, threw it into the Bedrock ecosystem, and told it to build a visualization and describe exactly what we accomplished. So that's what I would describe as an enhancement of something that is already doing a great job. So we already have software engineering best practices, we already have analytics best practices, but the cherry on top of the sundae is to take the new Gen AI tools and enhance what we already have. So that's really the lesson for this particular course, is that build a strong foundation, and with AI, you can take it to the next level. AWS Advanced AI Analytics. We're going to talk about many services, including Bedrock, which we see here, Amazon Q, SageMaker, Data Wrangler, and QuickSight. All of these work together to promote actionable business insights. And we'll also get into some performance optimizations with Lambda, which is also very critical for cost optimization. And we'll also talk about emerging research. So beyond Bedrock, we have Q here, which is for NLP, SageMaker, Data Wrangler for transformations, and QuickSight for intelligence. In terms of the Amazon Bedrock architecture, the key takeaway is that it's a unified API that's serverless for multiple foundation models, although you can provision dedicated I/O. In terms of security, it has the best practices that many services already use, like VPCs and IAM controls. We also have the ability to do model customization and fine tuning, and even distillation. Serverless is a key component here because it allows us to not have to worry about some of the finer details, and we can just start calling the API and more dealing with token level scaling. So Amazon Q Query Intelligence is a natural language service that has deep integration with many different components. The multi-service integration is a big part of what Amazon Q does. For example, if you open up Cloud Shell, it has integration with chat and also the ability to help you build command line tools. And also you can use it as a development environment, amongst other things like security. In terms of context aware processing, this is another key component. So it knows the problem you're working on when you're working on it, and it has the ability to do response synthesis. So what this means is that you have the ability to take multiple inputs and come up with a conclusion. And in terms of Data Wrangler pipeline, this is an automated data transformation service. Some of the things that it does include automated data transformation, intelligent feature engineering, and also quality validation gates as well. So you can say, for example, these are the specific metrics that we care about. Things have to pass those metrics before we can go to the next stage and go to the ML ready pipeline. The ML ready output streams allow you to validate that what has been processed through the pipeline is finally ready to be trained on. Now, QuickSight visual answers allow you to ask business questions and then get results like charts or maybe anomaly detection. And if we look at the connection with live data, this is also a very important feature of the platform. It can reveal hidden patterns through things like clustering and anomaly detection. And it also allows you to have a driver for decision making, because you can have a dashboard that comes from a software engineering pipeline or a business intelligence pipeline or product management KPIs, and that's how you can drive the actions. Now, in terms of the performance, one of the areas in analytics and data engineering that's a hot topic is, what language should I use? And some of the emerging research shows that Rust can be a huge performance gain, especially in the era of generative AI, because it's easier to write code, and memory efficiency definitely plays a role. You can see that cold start times as well play a huge role, because with Python, oftentimes you're using a container runtime because it needs a bunch of packages. With Rust, it's a small binary. Request latency, if it's a very efficient language like Rust, there'll be low latency. And then in terms of cost optimization, we have some benchmarking that I'll show that shows how you can reduce cost by, let's say, 90%, depending on certain workloads that are computationally expensive. The unified analytics flow is about doing things in a way that allows you to make decisions across all of the context of the data you have. So what this means is cross-service data flow. And what this really comes down to is being able to look at a dashboard that shows you what's happening with more than one service. This is automated processing as well. So if the results are coming in an automated fashion because it's clean data, then you're going to be able to make these dashboards. The real-time integration is another key component of modern analytics pipelines, so you can make actionable insights without having to wait for a day or a week. And then if we look at scalable architecture as well, this is an important component, especially using serverless technologies. So the next emerging horizons for analytics pipelines around AI could include things like neural search. This is an important component to consider. Also, zero-shot learning, quantum-ready API development, and then automatic optimizations as well. So maybe automatically fine-tuning or automatic dashboard creation. These are some of the emerging horizons that we're seeing as well with analytics and data engineering. An emerging area of using large language models is to outsource some of the analytics operations that an organization would do by using a foundational model. In this case, we're going to use Bedrock. We're going to use some analytics workflow. So this is more of a proof of concept just to get some of the end-to-end pipeline working. And if I take a look at the README file here, you can see that this is a project in Rust that calls into the Bedrock Foundation API and bases a forecast on sales data from a CSV. So first, we would need Rust. We would need AWS credentials configured. You need an active AWS account and also the AWS SDK. And then you would go through here and do a forecast based on this sales data. So let's go ahead and take a look at the sales data. Again, a very simple kind of intentionally contrived data for this demo. And then if we look at the cargo.toml file, this is where we're able to pull up everything that we need for the project. So in here we have the AWS config, and this is going to feature behavior versions latest, which is something that we're using in order to talk to the API. We also have AWS SDK Bedrock runtime. So the Bedrock runtime is going to use the foundation model, and we're going to talk to Claude using this runtime. And then we have Tokyo, which is a network operations library for doing non-blocking I/O. That's async. We also have the Serde JSON, which is a open source standard here for dealing with JSON. And then we have CSV library to deal with the data. So once we've got this all set up here, the only other thing to take a look at is the main, and we can go ahead and walk through what that looks like. You can see here's all the use statements. These are going to use all of the things in cargo.toml. And then we have a main here that uses Tokyo so that we can make these async network I/O calls to the AWS SDK. We go ahead and we load the configuration. We create a Bedrock client. We can then go through here and read and process the CSV file. Now, this is where it's kind of interesting, is that depending on what kind of operations you would outsource to a foundation model, we're going to first calculate some stuff local. We're going to figure out the total sales, the average sales. So we're doing some of the actual calculation in math first before we use generative AI, and then I prepare a prompt. So this would be something where I would say, in a simple scenario here, this works reasonably well. Here's the sales figures. Go ahead and give us a uh, analytical summary and forecast, especially as we're getting better and better at dealing with visualizations. Like this could be a great tool for doing some kind of fancy or custom visualization. But you also may want to have a more complex prompt here with JSON validation and treating the prompt more like code. But for now, this is a pretty good demo. And then here's the actual request itself. And so this is going to be sending this payload over to the AWS Rust SDK. So you can see your prompt, max tokens, temperature, top P, also which version of Anthropic. We're going to use Bedrock 2023 531. And then the body converts it into a string. And then we send this prompt to Bedrock. And then if we call Bedrock here, this is where we're getting the response. And then we go through and we print it out right here. So if we want to look at the tree structure, what I typically do in a Rust project is do tree space dash capital I space target. So exclude the target. Let's just look at what we've got here. Cargo.2ml. We have a data directory for sales.csv. We have a README, and we have a source which is the main.rs. So in order to run this, we just type in cargo run. And what it's going to do is going to go through here and send this prompt to Bedrock and says, here's the sales figures. And there we go. We have a response that says, okay, let's analyze this. The total sales for the past quarter were 4,500. The average forecast, since we know this, we can say within 3 months, the forecast will be 4,500. So this is kind of a naive forecast that we're getting from this. We don't know in the future what advanced analytics capabilities will come from foundation models, but as a good kind of proof of concept to go end to end to do analytics, I think this Rust plus Bedrock example is a pretty reasonable way to maybe start to get the foundations working for later enhancements and potentially even increasing things for visualizations as well. So I think that's really where I see some of the next stuff happening with data science and analytics, is to think about doing visualizations programmatically, but maybe keeping a lot of the math and foundational portions of your code locked into something that's deterministic. Here we have a Python Rust performance race. In this example, I have a Fibonacci computation, and we run it in Python, and it takes 13.5 seconds. In Rust, it's about a fifth of a second. And if we do a simulation, you can see that it's just running laps around the Python version of the code. And there's a pretty big difference in this particular version. So you can make the argument, well, just use some other C library or rewrite it in C, etc. But you could also make the argument, why not just use one language? Why not have to deal with packaging and have a binary that is extremely fast and also very secure because it's a modern compiled language? So there are some pretty significant problems with legacy scripting languages like Python that Rust fix. So how would we do this? Here we have DeepSeek, and in this case, DeepSeek allows us to paste some Python code in, and we can say, convert to Rust, for example. We can say, this is slow. Give me a Rust version without cargo. And it'll go through here and go, here we go. Here's your Rust version. We can copy paste this, and we can get it to run approximately 26 times faster. We could also do the same thing to Claude, right? We could say, make this a standalone Rust binary without cargo. And we could convert this, and it'll go through it and give us a Rust version. So this is something that generative AI assistants are very, very good at, is giving you a conversion from one language to another. And with the Claude tool, with DeepSeek, these are two solutions that I think are definitely worth exploring when you're dealing with low performance code in Python. All right, so this is kind of the traditional, thing that you deal with when you're trying to figure out optimization is people are like, "Hey, you better show me exactly what you did. I don't trust you." And in this case, we have a Fibonacci statement here, and what we can look at is that it's using just standard library. We're not doing any kind of optimization or fancy coding. This is just really simple brute force Python code, intentionally simple, so that we can make it, essentially computationally expensive. And so, how would we run this? We can just type in Python and then do Fibonacci 40. And what we'll see here is that this thing starts really grinding when we're running this. My machine starts to fire up a little bit. I hear it, taking a CPU core and saturating it, and it's a very slow computational process. At the same time here, if we go over to Rust and I take the code that was given to me from any kind of modern generative AI assistant, you can see it's able to build something that's very similar, style essentially, with maybe a little bit of difference because it's a compiled language. And then all I have to do is do Rust -O. So I want to optimize this so it creates a fast binary. And then I can just go here and I can do Fibonacci and I can do 40. And it's pretty obvious that there's a difference, right? Is that the Python version took a long time. If we time this one, you can see it takes just about 22 seconds. So there's some pretty significant differences when you're doing code that's compiled in a modern language like Rust or Go versus Python. And this is where generative AI tools really do play dividends. And it's worth seeing if some of your scripts that maybe you've taken for granted that are very slow, whether you could just do a copy paste fix and get something like, 60 times better performance just by using a conversion from Python to Rust. Today, we're going to explore a critical question in cloud computing. How much does a programming language choice actually impact your bottom line? We've created this visualization to demonstrate the striking difference between Python and Rust performance in AWS Lambda functions using real benchmarking data from a synthetic Fortune 500 workload. If you look at this corporate building at the very beginning here, you can see it's processing millions of Lambda invocations daily, and the two pipelines are feeding into the system. Python is in blue and Rust is in orange, and the thickness of the pipes is representing the amount of resources they consume. So from a monthly cost perspective, you see that $1.5 million per month with Python, but with Rust, we have $150,000 per month. So a 10x difference because of the compute. And this isn't just theoretical. This is a real world benchmark that I did that is reproducible. And if we extrapolate that out to 3 billion monthly invocations, we can see that this cost profile makes sense. Here, what we have then in the money pit is a striking visualization of wasted resources. So many organizations are thinking about reducing headcount or doing some other kind of trimming of the fat. But really what they could be doing is making their systems more efficient versus looking at reducing headcount. And this 1.35 million example, it's not just a number, it's literally falling from the infrastructure every month because it's running a language that is not as efficient as Rust. And so this isn't just a small optimization. We're talking about enough yearly savings to fund maybe even an entire engineering department. Now let's take a look at why this cost difference exists. If we look at the performance race at the bottom, we have two tracks. Python in blue is competing one task every 10 seconds, but Rust is able to compete a task every single second. And so over a 60-second window, and you can see here, this running over and over again, Python will complete only 6 tasks, but Rust will complete 60. So the same computational load, same AWS resources, but very different results. So what we're seeing here is that the collection containers on the right This is maybe the most powerful part of the visualization is that they're collecting all the tasks while Python is failing to complete them. So in a real world scenario, it means faster response, lower latency, better resource utilization. And the business impact is that we have a 90% cost reduction potential, 10x improvement in processing speed, better scalability during peak loads, and also more predictable performance. So if you're thinking about what you can do to save your organization in terms of business efficiency, looking at the computational components of your data engineering pipeline and your analytics pipeline is a great place to start. Energy efficiency is a very interesting problem in the world of AI and ML pipelines. And this visualization quantifies the computational inefficiency propagation in these AI and ML pipelines based on this empirical research shown in the 2017 paper. If we look at a base comparison analogy, this is like an automotive scenario, right? Where you have a 73 times efficiency difference between Rust and Python. You could think of a Chevy Suburban, for example, a 1968 Chevy Suburban that has 10 miles per gallon. And this is like Python, which is a high interpretive overhead. So it's really a language designed for experimentation and an interactive interpreter, not for runtime. If we look at a Prius Prime, this has the equivalent of 730 miles per gallon. And so this is a zero cost abstraction, right? It's a hybrid car that has extremely low mileage, and it's a futuristic design. So both paradigms can be optimized, but you still have the architectural constraints remaining. You cannot make a Chevy Suburban the same as one of these hybrid cars that gets incredible mileage. So the core insight here is that the research demonstrates this 73x base efficiency gap between an interpreted and compiled language, especially these modern compiled languages like Rust. And this expounds when you're doing exponential workloads. For example, AI is taking workloads and parallelizing them, and you're getting this loss of efficiency going over and over and over. So what does this mean in terms of AI analytics? Well, in the core function, you're already at 73x single operation and efficiency. And then you get into a pipeline, and now you have sequential composition effect here, 73 times in. Then we have batch, so we have 73 in squared. So we have parallel execution scaling. And then with a fleet, you're getting into a distributed compute amplification. So the problem is when you're dealing with a core energy efficiency problem like a 1968 Chevy Suburban, and let's say you built this into a taxi fleet, you cannot get away with that core inefficiency. No matter what you do to those Chevy Suburbans, once you start scaling it out, you could make them lighter with a new shell or put new tires on them, or maybe make them run less trips, or etc. But the core problem is it's a 1968 Chevy Suburban. So likewise, what this means in terms of research implications is that while Python optimization is valuable, hey, let's go ahead and let's optimize this, or memorize this, or build some kind of C version of Python. The fundamental architecture constraint is that the training costs scale cubically, the inference latency compounds linearly, and the resource utilization expands exponentially. So what this means is that in terms of looking at a language choice in AI ML, it's not just about the development velocity, especially in the era of generative AI tools. It's about computational sustainability at scale. And some of the things to think about would be, how can I move towards these modern languages, and think about energy efficiency, not just ease of development, especially in the era of these coding assistants. Why am I using a operational inefficiency for everything that I do? Today, I'm going to walk through a visualization of an AWS AI-powered code optimization pipeline. This pipeline leverages AWS services like Amazon Bedrock, Amazon Q, SageMaker, Data Wrangler, and QuickSight to analyze, optimize, and visualize code performance. Let's dive into each stage of this pipeline. First up, in the pipeline overview here, this pipeline consists of 4 key stages, and they're powered by different AWS services. The flow starts with code analysis, then it moves to intelligent code transformation, and then it goes to processing performance data, and then ends with visualization and insights. And these animated lines are connecting the stages, representing the seamless flow of data insights between these services. If we look at Amazon Bedrock code analysis, this first stage is powered by Amazon Bedrock. The AWS code analysis engine here is Claude, and it's going to look at the code base to identify inefficiencies and areas of improvement. And the code window represents the dynamic nature of this analysis. Bedrock is providing actionable insights that feed into the next stage of the pipeline. Amazon Q, or the intelligent code transformation step, is going to use those insights from Bedrock and refactor the code to optimize performance and reduce cost. And the background is going to symbolize the AI-driven transformation happening in this stage. And this is where the magic of the generative AI system comes into play, because we're automating what we would traditionally do in a manual and time-consuming way. Next up, we have SageMaker Data Wrangler, and this is doing performance data processing. And this processes the performance data that was generated by the benchmark earlier, and it looks at whether the pipeline is efficient and scalable. And the code window here is going to represent the data transformations occurring in this step. And Data Wrangler would prepare that data for the final stage. In stage 4, the QuickSight, or performance visualization stage, we have the metrics visualized, and the green animated path is going to represent the flow of data into actionable insights. QuickSight's then going to help developers, stakeholders understand the impact of the optimizations through these interactive dashboards and visualizations. And then this is where we get into actionable and also key insight-driven data science. If we go to the performance metrics panel here, you can see at the bottom, we have the KPIs essentially. We have the Lambda cost reduction, 40%, Rust versus Python runtime, 35%, memory utilization, processing speed, right? These are all the kinds of things that are theoretically applied. And really what we look at when we look at generative AI is that it is playing a critical role, but it's an enhancer. And so it's analyzing code with Bedrock, or transforming it with Q, generating visualizations with Claude and QuickSight, and then enhancing the stop. And it's not going to replace any traditional process, it's augmenting them to make them faster. So the key takeaways are that AI enhances traditional workflows. It's an end-to-end optimization as well, because it integrates the AI services and lets us analyze, transform, and visualize. And then the visualization lets us take action. So for example, using QuickSight to communicate insights and decision-making. And then finally, with cost and performance, we can lead these insights into cost savings and performance enhancements. So really that's it for this particular course. Thank you for listening, and I hope you can apply these techniques in your own project.